Hey guys, in this video we're going to be proving Euler's identity. So Euler's identity comes from pretty much complex numbers that if you have e to the I pi, that should be equal to -1. I'm just going to zoom in real quick. There we go. So this here is Euler's identity. So e to the I pi equals -1. We're going to try and prove this using a Taylor series. So a Taylor series pretty much approximates functions using polynomials. So the general formula for a Taylor series is given below. So if you have y of x, that's approximately, well, it's actually equivalent to y of x sub 0, where x sub 0 is the point you want to approximate it around. So it's like the chosen x value where you want to start approximating, plus y dash of x sub 0 multiplied by x minus x sub 0 plus the second derivative over 2 factorial multiplied by x minus x sub 0 all squared, and you can kind of see this pattern where it's coming. So this would be 1 factorial, and this would be to the power of 1, and this here would be to the power of 0 over here, so that's why that cancels out. So it's pretty much taking the derivatives, dividing by that respective factorial of the order, multiplying by x minus x sub 0 to that order as well. So in other words, to finish this off, it's the sum from what we at 2, so n equals 3 to infinity of the y to the nth derivative of x sub 0 all over n factorial multiplied by x minus x sub 0 to the n. So this is the general formula for a Taylor series. Now we're going to be using this to help us with our proof. So to start off with our proof, we're going to assume Taylor series is true. We don't need to prove that or anything like that. So I'm going to do is just take the formula and just make it pretty small so we can fit it all on one page. Right. So the way we're going to start this is we're just going to take a look at the exponential function, so e to the x. Let's try and represent this as a Taylor series. So the first derivative is just going to be e to the x, and so on and so forth. So the second derivative is itself. This comes from the property that the steepness of e to the x, this particular exponential curve, is itself. So no matter how many times you differentiate it, you're going to keep getting the same function. So that's really useful to us when we have our Taylor series. Now we're going to approximate our Taylor series around the origin. So x sub 0 is going to be 0. Okay. So let's just straight off give our Taylor series for the exponential. So x sub 0 is going to be 0. And we have, alright, y of x, which is e to the x, so we'll just write this here, is equivalent to the first derivative. So that would be e to the x to the power of x sub 0, which is 0. Plus the first derivative, the function is here, then it's the first derivative, so e to the power of 0 multiplied by x minus 0 to the 1, all over 1 factorial, subbing the rest in. Second derivative of itself is still e, subbing in the 0, x minus x sub 0 all squared over 2 factorial, and you can kind of start to see this pattern starting to emerge. So if I kept going, you would see a clear pattern starting to appear. So I'm going to make that as small as possible so I can keep this all neat and tidy-ish. Alright, so this keeps going on and on forever. So this means we get eventually this polynomial here. So e to the x is represented, e to the power of 1 is 1, e to the power of 0 is 1, plus x, because 1 factorial is just 1, so it's just going to be x here, the first term. This here will be x squared on 2 factorial, plus x cubed on 3 factorial, and it keeps going on and on. So this is the Taylor series for an exponential curve about the origin, where you start doing this. Now, instead of keep writing on forever, I'm just going to approximate it using a sum. So sum, continue at n equals 6 to infinity, x to the n all over n factorial. Okay. Now, if you went to infinity, this polynomial would be exactly the exponential curve. Okay, so that's really important for us because in our proof, we're going to be proving an exponential certain input. So when x is equivalent to I pi, gives you -1. So it's important that we have this Taylor series set out. What else we're going to have is we're going to have the sine and cosine function Taylor series because they will become useful later down the track. Okay, so now we've got values there. Let's copy this Taylor series formula so I can bring it downward without rewriting it a couple times. Right. So You're probably wondering why we need those. Well, sine and cosine functions, they're very close to complex numbers, which is actually where this formula arises. So it's going to be very useful to have those Taylor series. So y equals sine x and y equals cos x. So we want to approximate this function and this function here using a Taylor series. So pretty much an infinite polynomial. So we're going to start off with this one. So the function is just sine x. The first derivative is going to be cos x. And we're going to approximate it around the same point. So x sub 0 is 0. And same with this one here. The second derivative is going to be negative sine x. And then you differentiate that again, you get negative cos x. So you start to see a pattern starting to appear here as well. Trig functions cycle through the more you differentiate them. So this will be negative cos x. And then if I were to differentiate that again, I would get back to the start. So we're only going to differentiate to 3 here, and then we'll do the same thing here. So y equals cos x. The first derivative of that will be negative sine x. The second derivative of that will be negative cos x. And then the third derivative, so any derivative higher than 2, start writing it's not really a subscript, it's like, it's not a power, don't confuse that with the power, that's a derivative because of the brackets I've put there. So that's going to be sine x. Right. So let's do the sine function first. So x sub 0, if you plug that into the first term here, so when x sub 0 equals 0, you're going to get 0. Plug in x sub 0 equals 0 into here, you're going to get 1. Plug it into here, you're going to get 0, and here you're going to get negative 1. Okay? Because sine of 0 is 0, and cos of 0 is 1, due to the unit circle, which we've done before. So the first term in our Taylor series here, so let's just move cos out the way for a second. So our first term is going to be sine x, which is our function here, is equivalent to x of 0, which is 0, plus the first derivative, which is 1, multiplied by x minus 0 to the 1 on 1 factorial, plus the 0, which is the second derivative. Then we go straight to the third derivative, which is going to be minus 1 times by x minus 0 to the 3, all on 3 factorial. And then if we kept going, we'd start to see another pattern emerge. So we would then get plus 1 x minus of 0 to the 5 on 5 factorial, and then we would get a minus again because it's going to oscillate between 1 and negative 1 because of its derivatives. Because any value of 0, if you put that in, if cos is 0, it's going to be 1 or negative 1, depending on the sign in front of the cos. So it's going to oscillate between positive, and then negative, which is going to be 1 x minus 0 to the 7 on 7 factorial. And you notice all the even terms will cancel out because they will all have signs, and signs of zeros are just 0. So our Taylor series for sine x is going to be 0 plus x plus, minus x to the 3 on 3 factorial plus x to the 5 on 5 factorial minus x to the 7 on 7 factorial. Now, it's kind of interesting that sine is an odd function, and that Taylor series is represented with odd polynomials. That's quite cool. So we'll just leave that as a dot 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 there, because the sigma for it's quite complicated. But we know what it's doing pretty much. So that's the Taylor series for sine. Now let's take a look at cos. So let's go to the side real quick. And let's take a look at this. So when x sub 0 is 0, this is going to be 1, this is going to be 0, this is going to be negative 1, and this is going to be 0. So our first term is going to be, our function's cos x. So cos x equals, what's our Taylor series formula? I'm just going to move it up here because I don't want to write it out a million times. So our first term is going to be 1 plus, that term's going to be 0 plus negative 1 x squared on 2 factorial. So minus 1. Then it's going to be plus x to the 4 on 4 factorial. And then plus, well, it's going to be a minus, so minus x to the 6 on 6 factorial. And then it continues to do this as well. So you can see we get a pretty similar pattern appearing for cos as well. And it's pretty cool here because cos is an even function and it's also represented as an even polynomial. And you might think, what about the 1? Well, that's just a 1 times by x to the 0 here. So that's technically even, but let's just not talk about that. Okay, so we've got our Taylor series for both of those there. So now we can write them out quite neatly over here. So I'm going to zoom out so I can get the cos. Yeah, where'd it go? Sorry, I lost my place. Ooh. And if we wanted to, we could approximate those on any calculator, like on Desmos or anything, and you can see that they're slowly equivalent to each other over time. Okay. Now we've got those. Do we have everything we need to make our approximation? We just need this one up here. Okay. So what we're going to do is we're going to bring this guy down here as well, and then we can start our proof, because we've done all the hard yards now. We've got all our Taylor series that we need for the proof. All we got to do is pretty much start using it. So I'll bring this guy, oh sorry, bring you there. Alright, so now we have everything we need, but we're trying to prove this here. So e to the pi I is -1. So what we're going to do is we're going to let x equal I pi, okay? Or just to make it simpler, we're just going to say x equal, like let's replace this. This can be anything here, so we'll just replace it with ix instead. Multiply every bit of x by I. So what that turns into is this sum here. So e to the I x is equivalent to 1 plus, well, ix plus ix all squared, 2 factorial, plus ix cubed, 3 factorial, plus ix to the 4, 4 factorial, and so on and so forth. Now the reason I wrote out 5 terms is you can see a pattern will start to emerge and it will make it easier to visualize the proof. And now all I'm going to do is replace the x here with just ix to the n. Because all I'm doing is replacing x with ix, which is a valid substitution because it's still a function. You can input anything even though it's an imaginary unit. Okay, so what's going to happen here? So this here, that will be distributed, so you have I squared over x squared, but we know I squared is equivalent to -1 because I is defined as the square root of -1. So this here is going to turn into negative x squared over 2 factorial. So we can rewrite that there. So we'll go e to the ix equals 1 plus ix minus x squared on 2 factorial. Here, because I cubed is the same as I times I squared, this is just going to be negative ix cubed on 3 factorial. This here is going to be positive 1 because I to the 4 is the same as I squared times I squared, and we know I squared is -1, so -1 times -1 will be positive, so we'll have positive x to the 4 factorial. Okay. Here we're going to have the same thing. We're going to have positive times I, so that's just going to be plus ix to the 5. Okay. And then it starts to repeat itself. So the next term will be negative x to the 6 over 6 factorial, and then it will be minus ix to the 7, etc., etc. But I'm only going to do it to 5 because that's the only ones where it's most relevant. Plus the sum term. Oh, my sums are terrible here. Alright, let's see if we can do the better one. There we go. That's good enough for me. Right. So what do we see here? We see we have a group of just random junk pretty much. We've got eyes, we've got all sorts of rubbish in here. What we're going to do is we're going to group the imaginary and real units. So real and imaginary. So imaginary units are any bits that have I attached to it. So for example, that's an imaginary unit, that one is, and so is that one. So we're going to start grouping them together. And we'll group the real terms as well. So the real terms, e to the ix, is equivalent to, let's just put them in brackets. So let's say this is all the real terms here. Is going to be 1 minus x squared 2 factorial plus x to the 4 factorial plus dot 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 dot. Oh, it's going to be minus next anyway. Minus dot 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 dot. So that's all the real terms there. Plus, and then I'm going to take a factor out of I because all of them will have I included. So this will be x minus x cubed on 3 factorial plus x to the 5 on 5 factorial minus dot 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 dot, all those terms there. Now you can see what we have here is exactly our sines and cosines. Hopefully you can see that this bit here, so I'll bring this entire bit down so it's much more obvious to see. This infinite sum we have in here, oh, move that there, and we'll get the cos one while we're at it as well. Oh. Copy. So we'll place that there. So hopefully you can see that this orange bit here is going to click in exactly here. This is an infinite sum, which is exactly the Taylor series of cos x. And this bit here is exactly the Taylor series of sin x. Now you're probably thinking, what about all those dot dots? Those dot dots just represent the rest of the terms, just like these dot dots here. It's an infinite sum. If I kept going, the next term would be x to the 7 on 7 factorial. And you could keep going, and you'll get the exact same thing here. But I won't do that because I'll waste the time in the video. So you're just going to have to trust me. Alright. Okay, so let's just, we can now just replace these infinite sums with just cos and sin x. So this means this bit here is cos. So e to the ix is equivalent to cos x plus I sin x. Righto. And we wanted to prove, this is our initial statement, e to the I pi is -1. So all we're going to do is replace x with pi. So e to the I pi, substitute pi into here, and pi into here. Due to the unit circle, we know that's 0, and we know this here is -1. So therefore, e to the I pi is equal to -1. And that is the proof done. It also proves this cool formula, which is Eulers' identity. It's another identity that comes... Actually, this identity is probably more cooler than this one, because this one is just one extension of this thing. But anyway, that's what I'm going to put in the thumbnail anyway. Alrighty, hopefully you enjoyed that video. If you have any questions, leave a comment, and yeah, I'll try my best to answer it. Okay, thank you.